Assalamu alaikum. The article is angular velocity ratio. The angular velocity ratio definition is written here, and it is usually denoted by m subscript v in this textbook. It is defined as the output angular velocity divided by the input angular velocity. So important here is that what is the output? Output actually it is the rocker link, which is usually denoted by the digit subscript 4. This 4 subscript is actually used for the rocker or the output link, because output is achieved at the rocker link. So output angular velocity means the angular rotation of the rocker link about its grounded pivot O4. The angular velocity of this output link is usually denoted by the omega subscript 4, and that is the output angular velocity, and divided by the input angular velocity. Input angular velocity is actually the rate of rotation of the input link, and input link is usually denoted by the subscript 2. So the omega 2 is actually the angular velocity of the input link or the crank. So this ratio or angular velocity ratio is actually omega 4 by omega 2, and actually this ratio relates the output and input angular velocities mutually. So here it states that we can derive this ratio for any linkage. So this was the definition, and now the we can create a heading, that derivation of the angular velocity ratio. So we can derive this ratio for any linkage by constructing a pair of effective links. So here it says that the pair of effective links is shown in figure 6-10a. So let us see the figure. So this is the figure number 6-10a, and here we can observe here that this is a general 4-bar mechanism. This is the grounded link, this is the crank or the input link, and this is the rocker or output link, and this is the coupler link which actually connects the input link crank and the output link rocker. So let us again read the statement that says that the what is the definition of the effective links. So it states that the definition of the effective link pair is two lines mutually parallel drawn through the fixed pivot and intersecting the coupler extended. So that actually states that the effective links are actually two parallel lines which are which pass through the crank grounded pivot and the rocker grounded pivot. These two lines, for example here as the author has shown, O2A dash and O4B dash. So these two lines are actually parallel with each other. So these are actually the effective links. So as we can observe here that as the author later on states that here in this figure these effective links are actually parallel, but they are also perpendicular to the extended coupler or connecting rod link. So in this special case, the author has stated here that these are shown as O2A dash and O4B dash in figure 6-10A. Note that there is an infinity of possible effective link pairs because as we can observe that infinite number of lines can be drawn through these pivots O2 and O4 independently. So infinite number of lines can be drawn or can pass through this grounded pivot O2, and in a similar manner in infinite number of lines can pass through this pivot grounded pivot O4. So the necessary requirement for the effective links is that the two lines which pass through pivot O2 and O4, they must be parallel with each other and they should intersect this extended coupler link. So the distance from O2 to A dash and O4 to B dash, this distances will respectively be the effective input link. O to A dash will be the effective input link because O to A is actually the physical link. This is the practical or physical link as the apparatus is fabricated, but this is the effective link. So that will be explained later that what is the purpose of effective link. Effective links actually the purpose of effective link is that it actually the contributes in the angular velocity ratio. So the physical orientation of the actual link doesn't matter, but this effective link, this is actually this matters in the angular velocity ratio. So this effective link can be calculated in terms of this physical link. This physical link O to A is actually the physical link or practical link, fabricated link, and we actually are concerned with the effective link O to A dash or O4 B dash. So again the author states here, as we can observe, that they must be parallel to one another, but they may make any angle with the link 3, as we can observe here that the author states that these effective links O to A dash or O4 B dash, they must be parallel with each other, but they can make any angle with this extended coupler link. This extended coupler link means AB is the physical or fabricated coupler length, and this dashed line is actually the extended coupler link in both the direction of its location. So these effective links, the author states that they must be parallel with each other and they can make any angle, but for this special case these effective links are made perpendicular to this effective extended coupler link in order to make the simplicity in the derivation. So here the author has himself stated that in the figure they are shown perpendicular to the link 3 for convenience in the derivation to follow. The angle between links 2 and 3 is shown as V. So we must know that this angle, this is the input link and this is the coupler link or connecting rod link. which is denoted by uh, digit 3. As we can observe here that this angle is actually V, so the author actually assumes the acute angle which is less than 90 degree. As we can observe here that physically this is the AB, the fabricated coupler link. AB is the fabricated coupler link, and O to A is actually the fabricated input link. So actual angle is this, but as we can observe here that this angle is greater than 90 degree, means this is the obtuse angle. So for the actual angle which is considered, that is less than 90 degree, and that is usually denoted by this letter V. So V is actually the angle. If the angle between the fabricated coupler link and the fabricated or physical input link is greater than 90 degree, then we can simply say that we actually subtract that angle from 180 degree. So the angle that will be obtained after subtracting from 180 degree, that will be less than 90 degree, so that will be called as V. So we always take V which is less than 90 degree, means acute angle. So the transmission angle between link 3 and 4 is mu. So as we can observe here as well that this is actually the angle mu, which is the angle of transmission, and this is the angle between this extended rocker link and this extended coupler link. So as we can observe that this angle between this physical rocker link and the physical coupler link, this angle will also be equal to mu, because this angle and this angle is actually the vertical angles and they must be equal with each other. So in a similar manner, as we can observe here that this angle and between this line of the rocker link, this angle is also the angle of transmission, but as we can observe that the angle of transmission must be less than 90 degree in a similar manner as already explained for this angle V, which is actually the angle between the input link and the coupler link, that must be less than 90 degree. In a similar manner, angle of transmission must also be considered which is less than 90 degree, means if the angle between the rocker link and the coupler link is greater than 90 degree, so then we will be subtracting from that angle from 180 degrees, and we will be considering the angle which is less than 90 degree, means acute angle. So that angle will be treated as to be the angle of transmission. So both the angle V and the angle mu must be considered less than 90 degree or acute angles. So here it says that we will now derive an expression for the angular velocity ratio using these effective links, the actual link length and the angle V and the mu. So from the geometry, as we can observe here that O to A dash is actually O to A sine V. So here as we can observe that this is actually O to A dash, And here we can observe that if we consider the triangle O2AA dash, if we consider the triangle O2AA dash, as we can observe here that the angle at A dash is 90 degree, so this is a right angle triangle. So in the right angle triangle, this is O2A is actually hypotenuse, and this is actually O2A dash is actually perpendicular, and A dash is actually base. So this is perpendicular O2A dash, so that is actually the sine component of this hypotenuse. So that means O2A dash is actually O2A sine V, because this is O2A dash is actually the frontal angle in this triangle, so this frontal angle is called sine angle, and this sidewise side is called actually cosine side. So this is the sine side. So O2A dash is actually O2A sine V in this right angle triangle. So here the author has stated that O2A dash is actually O2A sine V, and in a similar manner we can observe that the effective link for O4B dash, which is actually if we consider that right angle triangle O4BB dash, where the angle at B dash is actually perpendicular, this angle is 90 degree here at this moment. So this is actually the perpendicular in this triangle O4BB dash, and this is the sine component, because O4B is actually the hypotenuse of this triangle O4BB dash. So these are actually the effective links, and as we can observe here that it says that state that from equation 6.7 we observe that VA dash is actually O2A dash omega 2. So equation 6.7 is actually that simply states that V, as we are familiar that V is equal to R omega. So as we can observe that O2A dash is actually the R. So that means the velocity that will be means O2A dash, when we will be multiplying the omega 2 with O2A dash, then we will be obtaining VA dash, because the angular velocity for the physical link and the effective link is actually same. As we can observe here that if the angular velocity of this crank link or the physical input link is omega, that means the angular velocity for O2A dash will also be omega. So this is actually O2A dash is R in V is equal to R omega, and omega is actually omega 2. So that means that the velocity will be equal to va dash, and that velocity va dash will be perpendicular to this effective link. And when it will be perpendicular to this effective link o to a dash, that means the velocity will be along the coupler link, this extended coupler link. So in this way, so as we can observe here that it states that the component of velocity va dash lies along the link AB as already stated, just as with a two force member in a force in which a force applied at one end transmits only its component that lies along the link to the other end. This velocity component can be transmitted along the link to the point B. This is sometimes called the principle of transmissibility. So here actually the author states that, as we can observe in the diagram, that this va dash, this component of the velocity v, as we can observe the velocity v, for a moment I can, for example, just capture this diagram in Windows Paint, and I can explain it here a bit. So let us paste it here, and here as we can observe here that, for example, actually this is the physical or fabricated link. So here, for example, I can use some different color, for example this green color, just to elaborate that this is actually, sorry, this is actually the, sorry, instead we can use this, sorry, this line here. So this is actually the velocity VA. This is actually the velocity VA, and this velocity VA is actually perpendicular to this physical crank, which is the input link. And as we can observe here that the angle of the crank with the horizontal is O2. So that means that if we resolve this VA into two components, one component along the this component is actually along the coupler link, and this component is perpendicular to the coupler link. So actually the author states that this component of VA is actually VA dash. So VA dash can be actually calculated in two ways. One way is that we actually uh, calculate the effective link O to A dash, and then we multiply it with the angular velocity to obtain VA dash as it has been explained here. This is VA dash. So the other method of obtaining VA dash is that we will be resolving this VA, which is the velocity of point A, absolute velocity of point A, into two components. One component is actually this line is a bit curvilinear. I have been unable to draw it straight due to some limitation or inexperience of drawing on this paint using this pencil. So kindly ignore it. So here my purpose is just to show that this component is along the coupler link, and this component is perpendicular. So actually this component is actually transmitted only from this point A to the output pin, or this output link rocker, which is denoted by the letter by the digit 4. So only this component, because this component is actually along the rocker line. So that means that the other way of calculating this velocity VA dash, that we will be resolving this VA into two components, one along the coupler link and the other component perpendicular to the coupler link. So here, for example, as we can observe that if this angle is V, so as we can observe that this angle between this velocity vector and this crank, this coupler link, extended coupler link, will be 90 minus V. This will be 90 minus V. So as we can observe, because this angle between this velocity V A and this crank is perpendicular or 90 degree, so that means if the angle between this extended coupler link and this crank is V, that means the angle between this velocity vector VA and this is actually 90 minus V. So that means because here the angle again is 90 degree, because this is the right triangle, because this component vector has been resolved into two components, one along the coupler link and one perpendicular to the coupler link. So that means this is also a right angle triangle. So this angle will be equal to again V. So as we can observe here that this component will be equal to VA VA and sine V. So as we can observe here that VA dash will be equal to, actually VA dash will be equal to VA sine of V. So this is the second method of calculating VA dash. So if we know the velocity VA, then we can simply take the sine, we can multiply the velocity VA with the sine of the angle V. So we will be obtaining VA, and the other method is actually mentioned here in this equation 6.11b, that is equal to O to A dash and into angular velocity. So if the angular velocity of omega 2 is given or known, then we can multiply it with the effective crank, then we will obtaining the VA dash velocity, which is actually the sine component, this component. So again, if any confusion, it can be proved that VA dash is actually practically equal to the same this component. So that can simply be proved here, that as we can observe that VA dash VA will be equal to actually O to A, means this is the crank and it's multiplied by with its angular velocity omega 2. So O to A omega, and then multiply it with sine V. So again, as we can observe here that O to A, as we can observe in this triangle, if we write O to A in terms of effective link, so that we can observe that this O to A is actually the hypotenuse of this triangle O to A dash. So that means that if we take the sine V, so sine V will be equal to O to A dash divided by O to A. So here I can again write, for example, just this is O to A and this is actually omega 2, and this now input the value of sine v in this triangle. So sine v is actually O2A dash divided by O2A, because the sine is actually perpendicular over hypotenuse. So input the value here that this is actually O2 A O2A dash, just input the line segment symbol and divided by O2 O2A. So as we can observe here that this O2A will be cancelled out with this O2A. So here will be left only O2A dash into omega 2. So as it has been proved that here that this O2A dash into omega 2. So here in this way it has been proved that VA dash is actually O2A dash, that VA dash is actually equal to O2A dash omega 2. So that in this way this has been also proved here. So here as we can observe that as the author has stated that this component of velocity VA dash lies along the link AB, and only this component is actually transmitted. So VA dash will be equal to VB dash, means that the component that will be along the coupler link, that will only be transmitted to the pin B, pin which actually connect the output link with the coupler link. So only that component will be 100% transmitted to the output or rocker pin if the pins are frictionless. So now as we can observe that from the question 6.7, as the author has stated that the input the values. So as VA dash will be equal to O2A dash into omega 2 in a similar manner, that is equal to the output VB dash is actually equal to O4B dash into omega 4. So after rearranging, as we can observe that omega 4, if omega 4 divided by omega 2 will be equal to O2A dash divided by O4B dash. So this is equation 6.11e. So this is one way of calculating the angular velocity ratio, means here this is the actually in the definition, this is the first way or method to calculate the angular velocity ratio, that we perform the velocity analysis and we obtain the angular velocity of the rocker link or the output link from the velocity analysis, complete velocity analysis, and then we will be taking its ratio with the input angular velocity omega 2, and that will give us the angular velocity ratio mv. So this is one method. The second method is given in equation 6.11e, that the same angular velocity will be equal to the ratio of the effective input link. As we can observe here, that this links ratio is actually the reciprocal of the angular velocity ratio. So angular velocity ratio is the output angular velocity divided by the input angular velocity ratio, whereas the effective links ratio is actually the length of the effective input link divided by the length of effective output link. So these ratios of the lengths of the effective links are actually reciprocal of the angular velocity ratio. So we must also know this fact. So this is the second way of calculating the effective links, that we will be drawing the parallel lines through O2 and O4, and those lines will actually be intersecting the extended coupler link, and we will be measuring or calculating from trigonometry the lengths of those effective links, and we will be taking their ratios and we will be obtaining the angular velocity ratio, and that will be equal to the angular velocity ratio as has been calculated from the omega 4 by omega 2 in the previous equation. So here again it says that if we substitute the O2A dash and O4B dash, means the length of the effective links in terms of the physical links, then we can observe here that is quite simple, that in the diagram we can observe that O2A dash is actually O2A dash is actually O2A sine V. So just we can input these values, that is actually O2A dash sine V and O4B sine mu. So this is also equal to angular velocity ratio. So this is the third way of calculating the angular velocity ratio in terms of the physical or fabricated lengths of the links. So we can again observe that this is also reciprocal of the angular velocity ratio, because the angular velocity ratio is the ratio of the output angular velocity to the input angular velocity, whereas the ratio is the length of the sine V of the physical or fabricated length of the input link divided by the sine mu of the physical or fabricated length of the output link. So here in the numerator is output angular velocity, in the denominator is the input angular velocity, whereas in the link lengths, in the numerator is actually the input link, and in the denominator is actually the length of the output physical or fabricated length. So these ratios are reciprocal of the angular velocity ratios. So this is the third way of calculating the angular velocity ratio. So in the exam any method can be asked for as a verification purpose. So in the next page, the author actually states that there is the fourth way for calculating that. Here it says that note in the equation 6.11f that as the angle V goes through 0, the angular velocity ratio will be 0 regardless of the value of the omega 2 or the link length. So let us explain this statement that as angle V goes through 0, the angular velocity ratio will be 0. So here, as we can observe, that if sine V is actually 0, that means as we can observe here, that when this crank will be rotating, there will be a time when this physical crank will be collinear along this coupler link. So then this angle V will be 0. This angle V will be 0. So that means when the angle will be 0, that means no component of actually velocity will be along this extended coupler link, as that can also be observed from here, that when this velocity Va will be equal to perpendicular to this link, that means the whole velocity will be perpendicular to this effective coupler link. No component of this velocity Va will be along this coupler link. So that means at that moment, there will be no Va dash or the velocity angular velocity ratio will be 0. As we can observe here, the angular velocity ratio will be 0 regardless of the values of the omega 2 and the link length, and thus omega 4 will be 0. When the angle V is 0, link 2 and 3 will become collinear, thus in the toggle position. Here we should also expect that the angular velocity of the link 4 will also be 0 when it has come to the end of its travel. Okay. Here it says that we should expect that the velocity of the link 4 will be 0 when it has come to end of its travel. Because that will be at its extreme, so that will be momentarily at rest. That here it states that an even more interesting situation obtains if we allow angle mu to be 0. So that state that equation 6.11 shows that omega 4 will go to infinity when mu is equal to 0 regardless of the value of omega 2 or the link lengths. We clearly cannot allow mu to reach 0. In fact, we learned in the section 3.3 that we should keep this transmission angle mu above about 40 degrees to maintain good quality of motion and force transmission. So that actually states here that if mu is actually 0, so that means something divided by 0 will be equal to infinity. So that means angular velocity of the output link will be infinite. So that is actually undefined, so that is not allowed. So here is actually the fourth way that says that figure 6-10 we show the same linkage as shown in figure 6-10a, but where the effective links have now been drawn so that they are not only parallel but are also collinear. So here in the figure 6.11b, as we can observe here, that these effective links means O2 A dash and O4 B dash are actually now collinear here, and as we can observe that from the linear graph or the using Kennedy's theorem, we observe that this is the instance at I2 comma 4 that can also be proved here. For example, I can just modify this diagram. Sorry, here as we can just I can draw here approximate circle here. This, for example, this is 1, this is 2, this is 3, and this is 4. So as we can observe here that first of all draw permanent instant centers like this. So now draw this diagonal 2 comma 4. So here as we can observe that the instance 2 comma 4 will be located on the line connecting the instance center I1 comma 2 and 1 comma 4. So this is actually permanent instance center 1 comma 2, and this is the instance center instant center 1 comma 4. So this is instant center 1 comma 4 and this is 1 comma 2. So this is actually the extended line, extended in a state. Just use this line, for example, here like this. Here like this. Here like this. And now thus use the second trial. This is instant center 2 comma 3, and this instant center is 3 comma 4. So extend just this line here. So here will be the intersection, and this is actually the instant center 2 comma 4. So here, as the author has also shown, that this is actually instant center 2 comma this is center 2 comma 4. So as we can observe here that the author has drawn like this. So I have also explained this. So here as we can observe that the angular velocity ratio in a similar manner, that will be equal to O4 divided by O2, that will be equal to this effective input link, as the author has explained here, that this is the effective crank. Now effective input link O to A dash, because actually A dash point and B dash are actually now coincident at the same point. So A dash and B dash point are both points at I2 comma 4. So here we can write that this the same actually instant center point A dash is also here. This is this is point A dash, and again point V dash is also same here. Actually I have very limitation to draw on this Windows Paint. So actually A dash and B dash point which were shown here, these are actually now coincident at instance 2,4. So this is the effective link O to A dash, and the effective link O for B dash is actually the sum of O to A dash plus this grounded distance, because O to O4 is actually the practical or physical fabricated grounded link. So we can just for example write it here that O4 B dash, or we can say O4 I2 comma 4 is actually equal to O2 A dash plus simply you can say D, because D is actually the ground link. So RO2 O4 are the length of the link number 1. So this is the fourth way of calculating the angular velocity ratio given by question 6.11g. So angular velocity ratio is O4 divided by O2. And next actually here it comes the mechanical advantage. So the author has stated that the mechanical advantage that says that the power P in a mechanical system can be defined as the dot or scalar product of the force vector F and the velocity vector V at any point. So here as we can observe that as power actually is a scalar quantity, and power is the dot product of the force vector and the V vector. And remember that force and V vector are in the same plane. For example, force is also in the xy plane and V is also in the xy plane. So that is actually simply their respective component, that Fx component of the force that will be along x-axis, and that will be multiplied with simply the component of the velocity in the x direction, and because they will be collinear with each other and the angle between these components will be 0. And in a similar manner the y component of the force and the y component or vertical component of the velocity So that says that for a rotating system, power P becomes the product of torque T and the angular velocity ratio, angular velocity omega, that in two dimensions we have the same z direction. Here important or interesting fact is that I questioned the students while in the class, that as we can observe here, that the power in the case of force and velocity vector is actually the dot product, but in this case the power in the rotational case is actually not the dot product of torque and the angular velocity vector. That is not actually the dot product, the author has not stated here. So what is the reason that we have not written here that P is like as we observed that angular velocity is also a vector quantity and T is also a vector quantity torque, so that could also be written like this: F dot V, that T dot omega. But what is the reason for not writing this equation of 6.12b like this equation 6.12a, means P is equal to F dot V? So why we have not written like this? So the thing is quite simple, that actually that power is actually simply equal to torque here in this case, torque here. And as we can observe that the torque has been already calculated, that torque unit is actually Newton meter, and torque is simply calculated by the force multiplied by perpendicular distance, which is equal to the moment arm, R denoted by R. So when torque will be calculated, so that means its only magnitude will be considered, and once torque has been calculated, that will simply be multiplied with the omega, because from omega the unit of omega is actually radian per second. So from omega, this torque value or magnitude only obtains the satisfy the units, means radian per second. So as radian is a dimensionless quantity, so that means Newton meter per second, which is actually Newton meter is actually joule, and per second is actually, so Newton meter per second is joule per second, which is actually power. So in this way dot has not been used. So that was simply interesting fact. Now go to the next equation, that power flows through a passive system, and as we can observe that in a passive system is such a system which actually contributes the losses, because the input power is not 100% converted into output power, because some losses are unavoidable and necessary losses always do take place. So mathematical efficiency that can be defined as efficiency is equal to power output divided by power input, means input power will be greater and output power will be lesser, because some losses will also be done, so efficiency will be less than unity. So here it's stated that linkage systems can be very efficient if they are well made with low friction bearings on all pivots. Losses are often less than 10%. So that means linkage are very effective. So for simplicity in the following analysis, we will assume that the losses are zero, i.e. a conservative system. So the conservative system is such a system in which the losses are zero, means input power is how 100% converted into output power. So then letting t in and omega in represent the input torque and angular velocity ratios, and t out and omega out represent the output torque and angular velocity ratios. So we can write it here that p in is equal to t in omega in, and p out is equal to t out omega out. So as we can observe that for the case of conservative system, power output will be equal to power input, means no losses will be there, as previously in equation 6.12. see, this equation is for a for an ideal system. So this is for an ideal system, and for a conservative system the losses are zero. So this is a passive system. In the passive system losses are always there. So we must remember that a passive system is such a system which actually suffers losses, power losses. So a system which does not suffer power losses, that is called the conservative system, means in which the input power is 100% converted into output power. So that means here this equation p out is equal to p in for a conservative system. So for the conservative system, t out omega out is equal to t in omega, and so that comes out to be t out divided by t in. So here again we can observe that the torque ratio, means the output torque divided by the input torque, is actually the reciprocal of the angular velocity ratio. So this is also a conclusion that the torque ratio, means the output torque divided by the input torque, is actually the reciprocal of the angular velocity ratios. So note that the torque ratio is the inverse of angular velocity ratio. So next comes the mechanical advantage. So here it states that the mechanical advantage can be defined as that ma is equal to F out divided by F in, means the output force divided by the input force. So this is the definition of the mechanical advantage. So here it says that assuming that input and output forces are applied at some radii r in and r out perpendicular, means these are the effective radii where the input and output forces are applied. So F out is equal to T out divided by R out, and F in is equal to T in by R in. So substituting equation 6.13b and 6.13a gives an expression in terms of the torque. So simply input the values of this F out and F in into the equation of mechanical advantage, which is 6.13a. So when we are inputting the values, so we will be obtaining that T out divided by R out will be multiplied by T in divided by R in. So after that we will be cross multiplying R, as we can observe here that numerator and denominator can be interchanged like this, that the denominator of T out, which is actually R out, that can be shifted like this, which is actually in cross multiplication, that T out divided by T in, because here this is F out divided by F in. So F out was actually T out divided by R out. So just actually these are written in terms of torque ratios and radii ratios simply, and nothing else. So mechanical advantage is actually T out divided by T in into R in by R out. So substituting as we can observe that T in T out by T in is actually equal to inverse of angular velocity ratio, or omega divided by omega out. So a mechanical advantage, the final formula for mechanical advantage is actually this equation 6.13d. So we must memorize this equation for practical purposes, for solution purposes, that mechanical advantage is actually omega in by omega out into r in by r out. So when we substitute the values of the angular velocity ratio in terms of physical link length, so this comes out to be m is equal to O4 b sine v divided by O2 a sine v r in by r out. So in this way, so here the author has actually made some conclusions. So here in this paragraph, the author has made some important conclusions about this equation 6.13e, which is the final equation for mechanical advantage in terms of the physical or fabricated link lengths and the effective radii of input and output links. So here it says that see figure 6-11 and compare equation 6.13e to equation 6.11. F. So actually this was the equation 6.11 F. This was the equation that O2a sine v divided by O4b sine mu. That means that actually that was the equation of angular velocity ratio in terms of the physical or fabricated length ratios in terms of sine v and sine mu. So that here actually states that as we can observe here that this ratio is actually the reciprocal. So here it says that equation 6.13e shows that for any choice of r in by r out, so that means for any choice of r in r out means that if for example the ratio of r in and r out remains constant, so this is the meaning of any choice of r in or r out, means for one test or for one checking ratio of r in and r out remains constant, so only the effect of this ratio means O4b sine mu and divided by O2a sine v ratio, the effect of this ratio is actually checked at that moment. So this is the meaning of any choice of r in r out. That says that the mechanical advantage responds to changes in the angles v and vu in opposite fashion to that of the angular velocity ratio. Because why? Because actually the angular velocity ratio was actually equal to O2a sine v divided by O4b sine mu, means that angular velocity was actually reciprocal of this term. So that means if this ratio O4b sine mu divided by O2a sine, this increases, that means the angular means if the angular velocity ratio is increased, mechanical advantage decreases, and if the angular velocity ratio decreases, mechanical advantage increases. So this is the meaning of this equation, that if this ratio, which is actually the reciprocal of the angular velocity ratio, if this ratio increases, mechanical advantage will be decreasing regardless of this ratio, because this ratio is constant. For example, while testing this ratio, and if this ratio decreases, then mechanical advantage increases. So that means that the mechanical advantage responds to changes in velocity angle in the opposite fashion to that of the angular velocity ratio. So that was the meaning. So that states that if the transmission angle mu goes to 0, so here it says that if the transmission angle mu goes to 0, so we observe that the mechanical advantage will become simply 0, as you can observe, which we don't want it to have. The mechanical advantage also goes to 0 regardless of the amount of the input force or torque applied. But in the case of we observed that in the equation 6.11f, that if the transmission angle goes to 0, then that means the angular velocity ratio will go to infinity. So that means in this case, the angular this ratio will be equal to 1 over divided by infinity, because the angular velocity ratio will be infinity when the angle of transmission will be 0, because in the equation 6.11f this term O for B sin u was in the denominator. So in the denominator was 0, so that means the angular velocity ratio or omega 4 was infinity or undefined. So 1 over undefined or infinity, that means 0. So that says that the mechanical advantage also goes to 0 regardless of the amount of the input force or torque applied. So but when angle V goes to 0, means when angle V goes to 0, that in this case as we can observe in the denominator will be 0, so that means mechanical advantage will be infinity. Means mechanical advantage will be undefined or very much large. But in the case of angular velocity ratio, when V was 0, then the angular velocity ratio was actually 0. So that means here it says that when the transition angle goes to 0, which we don't want it to do, that the mechanical advantage also goes to here. But when the angle V goes to 0, which it can and does twice per cycle in a Grashof linkage, so that means actually here as we can observe that this angle V becomes 0 when this crank O to A becomes collinear. In the extended case means when this AB will be collinear with this O2 A dash will be on the same straight line, and that will be the extended case here, and the other case will be the overlapping state. Means for example I can show it here, this thing. here like this, that here that there will be a time when this crank will be here. For example, like this, I can just make it here like this at a moment, and here like this. For example, I can change it in some other color, for example this color. So this is the extended, means this green color is actually the crank, and this cyan color or somewhat blue color is actually the connecting rod or coupler link. So here like this, so this will be the position. For example, just I can make it in black color. So this will be the when at this moment this angle V between this crank and this coupler and this crank will be 0 degree, or we can yes, 0 degree, because 180 minus 180 degree will be 0. So the other case that can also be drawn here, just for clarity, that here when in this state here, so at that moment, if in a similar manner, just I can draw here that in that case, for example, I can just so here like this. So at this case means this is the overlapping case, and that was actually the extended case. So that actually the author has stated here. In this equation, that here that but when angle V goes to 0, which it can and does twice per cycle, so that means when the crank will be completing one complete 360 degree, so at this extended case, when crank and coupler link will be collinear with each other, and other will be the overlapping case when the connecting rod or coupler link will be overlapping this crank link. So that will be twice per cycle, means after 180 degree revolution of the crank. So at 360 degree, that will be twice per cycle in a Grashow linkage. The mechanical advantage becomes infinity. So when angle V will be 0, mechanical advantage will be infinity and the angular velocity ratio will be 0, because the angular velocity ratio is O to A sin V divided by O for B sin mu. So when angular velocity ratio is 0, mechanical advantage becomes infinity. This is the principle of rocker crusher mechanism in section 11F. A quite moderate force applied to the link 2 can generate a huge force on link number 4 to crush the rock. Of course, we cannot expect to achieve the theoretical output of infinite force or torque magnitude, as the strength of the links and joints will limit the maximum forces and torques obtainable. Another common example of a linkage that takes advantage of this theoretical infinite mechanical advantage toggle position is vice grip locking pliers. So leave it. So here it says that these two ratios, angular velocity ratio and mechanical advantage, provide useful dimensionless indices of merit by which we can judge the relative quality of various link designs that may be proposed as solutions. So here in figure 6-11, this is shown here that this is the effective radius, input radius, and this is the force that is actually applied at by the link 2 at this input pin, means the input the common between this coupler link and this crank link. So here, as we can observe here, that this angle is actually, that means V is approaching to 0, means as soon as angle V will be 0, the mechanical advantage will be going to infinity. So here, as we can observe, that this is actually the effective output radius. So at this moment, output force will be applied to crush this rock in this way. So this is actually, this is the principle of the rock crusher mechanism, which is used in the to crush the concrete in road construction purposes. So here this article in this way has been completed.